Hi, I'm Doug Black. I'm editor-in-chief of Inside HPC. And today we have with us Dave Turek. He is the longtime IBM HPC strategist who left IBM in June and has moved over to Catalog, which is a Boston-based startup involved in DNA-based storage and computation. Dave is the CTO of that company. And Dave, for our viewers, explain to us the basics of what DNA technology, DNA-based technology is all about.
Sure. Thanks, Doug. So I think everybody is aware that DNA, of course, is a repository for genetic information. And that's been sort of the triggering idea for people for quite some time now, thinking about how it might store other forms of information as well. So that we know it works as a molecular representation or repository for data, if you will. So what Catalog has done is it's figured out a way to encode data into DNA by building DNA synthetically. So we're not talking about taking DNA out of a human or out of a cell, but actually in a laboratory, constructing DNA molecules from components of DNA, each of which is encoded to represent an element of data. And then as you string these pieces of DNA together synthetically and assemble them, you actually create content to the information, if you will.
Okay, so it's interesting for you coming out of decades in classical von Neumann-based computing to make this jump. Is this sort of one of these place DNA-based computation and storage in the continuum of some of these alternative architectures that are now being pursued by various companies and startups?
Well, I think if you look at it from a storage perspective, it brings a handful of attributes to the table which are distinctive. One, it's amazingly dense, so you could probably store all the information that exists in humanity in the size of a shoebox. Secondly, because of that, it's very energy efficient, and so you can escape some of the costs that cloud providers and others uh, uh, are faced with when they try to deploy conventional storage technologies. And under the right circumstances, it effectively can last forever. We've seen DNA from ancient animals and other kinds of living organisms that have been preserved over thousands or tens of thousands of years. So those are all very positive kinds of elements that are of great concern to some number of companies today. So there are companies that are actively engaged with us now, looking at how this technology might relate to the kinds of archival and storage problems they see forthcoming.
Okay, talk about to us about some of the more likely workloads that this type of technology might, naturally move toward.
Well, from a data perspective, the thing you look at are circumstances where there's a lot of data which needs to be preserved through time with fidelity and perhaps is read somewhat infrequently. And the reason I make that distinction is we're able, with inventions that we've done, write data very, very quickly. But the part of the industry that's focused on reading DNA data, the whole genomic sequencing community, is a bit slower. So innovation needs to take place there to get reads and writes in balance. So as it stands today, there is an imbalance in favor of writing compared to reading. So write once, read infrequently, that kind of thing. You'd see it in deep archive. You might see it, for example, in the oil and gas industry, where you're preserving data for decades as you're waiting for computing algorithms to catch up. You might look at it in simple repositories of human knowledge that are at risk because of physical degradation, something that you want to preserve effectively for eternity. And you can find that in social sciences. You can find it in a variety of other domains as well. Think of libraries and the work that goes on there with respect to digitizing libraries. But these digital forms also carry with them certain costs and other attributes which DNA might prove to be a superior kind of media, if you will.
And Catalog is not the only company in the DNA-based technology area. What is the point of departure? What's the unique take that you all have on this technology category?
So from our perspective, it comes first of all with a clever way to encode data into DNA to minimize the amount of chemistry that's involved. So we're not focused on base pair encoding of data. We're actually looking at encoding data in fragments of pre-constructed DNA pieces, if you will. So we have kind of a Lego kit from which we can choose pieces and assemble them to create the data representations we're looking for. So that's point one. Point two, we actually developed and invented a machine using inkjet printer technology with a partner called Cambridge Consulting out of the UK that actually can write the DNA pieces that we're talking about here. In effect, we're using inkjet printer technology to write data into DNA. So that incorporates an automation process step in writing DNA. And as a result, we think we're orders of magnitude faster than what anybody else has contemplated and order of magnitudes cheaper than what anyone else has been able to demonstrate.
Now, you did some work with Wikipedia. Could you talk about that project and the implications of that project?
Last year, the team pulled together with Cambridge Consulting a prototype machine and use it to write the complete English language contents of Wikipedia. And so you ended up with a small little container of everything that's involved in Wikipedia. It was a demonstration of the ability to both encode data, but also to read it back accurately. And it was through that process that we gained insight in terms of how to effectively scale up the machine technology and the automation steps to go at a dramatically faster speed than we were able to last year. So today we can do about a megabit a second in terms of data encoding. And we can do 20, 25 megabytes in about an hour, something like that, which is much faster than what anybody else has contemplated. Now, it's not fast enough, for example, to take over the world of data storage, but we have tremendous headroom in the technology in terms of both the evolution of the chemistry, the evolution of encoding schemes, and improvements that can be made from an engineering perspective into the machine that we've designed to write data into DNA. So we think that there are several orders of magnitude improvement in terms of performance and several orders of magnitude improvement in terms of cost efficiency that are within our reach.
Okay, and tell us how far away this is from commercial viability, and also you mentioned taking over storage. Do when this comes to maturity as a mature product, uh, what role do you see it playing within a typical customer ecosystem?
Well, with respect to the readiness of this from a commercial perspective, we are weeks away from commercial engagements in proof of concept kinds of studies in multiple industries. So the message, of course, is multiple industries are exploring this. They have different requirements, different needs, et cetera. But I would say, generally speaking, they are reflecting the exploitation of the kind of differentiated value proposition that's embodied in the storage of data into DNA. So small footprint, low energy consumption, um, longevity, fidelity, and so on. So that much is in place. Um, we think that this will expand dramatically as a result of these engagements, and we'll discover tremendously broader sets of opportunities by which we can pursue. But I would say there's another element to this as well, which we're beginning to think about, which is, can we actually inject computing into DNA at the same time as we inject this whole notion of dating? Now, I'm not trying to make a scientific argument here or a computer science argument, but I am saying that we think that there are ways that one can compute with DNA that can leverage the chemistry and the capability of encoding instructions, encoding data, and leveraging the ability to dramatically replicate DNA molecules to achieve certain advantages in terms of computational speed. So it's one of the threads that we're pursuing as we sit here today.
Okay, great. And now I believe we have some footage of the actual system, and I found uh, the system very interesting visually. It looks almost like a retro machine out of IBM mainframes of the late 50s. But Dave, maybe you could give us a bit of a guided tour of the hardware.
Sure. The video that we have depicts a machine in our Boston office, and it's sort of in a V shape. On the left-hand side, you have about 14 feet of a machine. The right-hand side is about 12 feet, and it's about 4 feet wide. On the left, down here in the lower corner, you see a spool of material. We call this webbing. It gets unfolded at about 16 meters a minute, and it passes to the next station where we have these read-write heads that actually write the DNA. The piece now facing us with the glass is where the DNA is incubated, and it finally concludes over to the right where chemistry takes place to cease the reactive elements of what's going on. The DNA molecules are stripped off of that plastic sheeting, and the content of the data now takes the form of DNA molecules stored in a liquid. So it's a collection of technologies that sort of depict the interplay of hardware, software, and chemistry all in one um, conglomeration of technology, if you will.
All right, very interesting. So, best of luck with this venture at Catalog, and be looking for information about those proof of concept projects that you have coming up.
Thank you very much, Doug.
Thanks, Dave.